Good morning, everyone. Welcome to our sixth session of our exercise. Um, Please let me know if you can hear my voice. I think the internet connection is not so well today. Can anyone give me a response if you can hear me?
Yes, we can hear.
Okay, thank you. So before we start, a kind reminder that about the presentation. The registration for presentation ended yesterday, but uh, there were only a few people who registered. So if you haven't registered, please, I opened the registration again. So please go ahead and register your group or yourself for the presentation. And the presentation will start on this Wednesday. Okay, so then we can take a look at our exercise questions. So today we are implementing Adaline algorithm to predict second column from the first column in this data set, rabbit data. Let's take a look at the data set. Okay, so the first column represent age of a wild Australian rabbit in days, and second column represents weights of their eyelenses. Do you think the prediction results are good? Why or why not? Do not use existing implementation of Adaline for this task. And if you have implemented the perceptron algorithm last week, it's a good place to start. So from this data set, we have two columns. The first column is in days, the days of a rabbit, and the second column is the weight of their eyelenses. And okay, it's a very simple data set. And let's get started. First, as always, we need NumPy and Matplotlib for visualization. Okay, so Adaline stands for adaptive linear neuron. It's a very simple and early single layer artificial neural network. So it's very similar to perceptron. It tries to learn a decision boundary or a regression, which is a relationship between inputs and outputs. The difference between Adaline and perceptron is that Adaline uses a linear activation function for its output, which means that the output is simply the weighted sum of inputs. The how Adaline update its weight is by it the weight update is based on the difference between the linear output and the actual target value, which is y, which is the y value. So it uses this rule called the delta rule. It is derived from minimizing the mean squared error MSE using gradient descent. So when we're comparing to perceptron, the perceptron update weights, like we have discussed this in exercise 5, the perceptron update its weights based on the difference between a threshold output and the target. So because the Adaline output is linear and it minimizes MSE, Adaline is more suitable for linear regression problems, such like this exercise, we are predicting the weight from age. After we have imported the libraries, then we can define an Adaline function. So you can see we have some similarities to the perceptron that we have defined last week. We have our input features X and target values Y. And we have our learning rate, our iteration, which is the number of epochs, and our initial weight. But this is optional. So when the initial weight is not provided, then we need to generate a random initial weight. And then we multiply it by 0.01, which makes them very small. And that's often a good starting point. So after we have generated the initial weight, then we need to add bias column to the input feature X. And this allows the model to learn an intercept term, which is in the formula we have discussed before, it will be represented as W0. Um, okay, the bias column here. So numpy ones, we are creating a column vector of ones with the same number rows as X. And H stack horizontally stacks this. Uh, H stack means it's to stack this horizontally. We're horizontally stacking this column of ones with the original X. So if the X was like this in this shape, H1, H2, then it becomes something like this, 1. And that's why we need to stack them horizontally. And then we can start our training loop. So for I in range of iterations, uh, we need to calculate for the first step in the iterations is to calculate predictions. This is a dot product of the input feature X and the current weight vector W. So in Adaline, the output of the neuron is this net input, which is the linear activation function. And then we need to update the weight using the Adaline learning rule, the gradient descent. So the core idea is to adjust the weight in the direction that reduces the error. Let's write the weight update rule first. Then we can explain a bit more. Okay, here first let's break down this update part. We can y minus predict. This is an array of errors for each sample. And then we reshape this error array into a 2D column vector. Then we multiply it by x. This is element-wise multiplication of the reshaped error with the input feature x. And this is related to the gradient of the square error with respect to each weight. And then we calculate the mean of these products across all samples along the axis of 0. This is basically means it's summing the contributions from all samples and dividing by the number of samples. So in this way, we are updating the gradient descent in batch, which is using all samples from one update. And then we scale this average gradient component by the learning rate. And then we add the scaled update. We add the scaled update to the current weight. So the W here, the new weight here, equals the old weight plus learning rate that's multiplied by the average gradient component. And then after we have updated the way, we can calculate the mean square error for this iteration. So MSE. Um, so this is a cost function. Adaline tries to minimize. And after all iterations, we return the final trend weights and the MSE from the last iteration. So we return the weight and MSE. Okay, that's how we define the Adaline function. If you're not so familiar with the update rule or the calculation, you can refer to the PowerPoint that we have uploaded to eLearn. They have more detailed explanations, or you can ask them like now. Okay, after we have developed, I've defined the Adaline function, then we import the data. the rabbit data. And for the input feature, we're selecting everything. We're selecting everything in column 0, which is the first column, as X and the second column as Y. And then we're reshaping the extracted data into a 2D array. And this is the reason we need to do this is because we need to be compatible with the Adaline algorithm, because the Adaline algorithm here expects a 2D input array. But for Y, we just select everything in the second column. Okay, everything looks good. Then it's our time to run the data through the prediction algorithm we have defined. Input, target, iterations. Let's iterate 100 times. And let's give it a very, very small learning rate. So final mean square error and final weights. Let's run it multiple times and see the results. But anyway, the result we're seeing here, we can see the mean square. We have a very, very high MSE value. The mean square error value is around 6,400. And this is a very high value, which suggests the model's predictions are not very close to the actual islands weights. And the weight for the age feature, this is the weight for the age feature. It's very, very small. It's 0.005 compared to the bias term, which is around 0.29. So there's also a huge difference here with the weights and the bias term, which suggests the model relies more on the constant bias term rather than the age feature to make predictions. So the results suggest this is at least with the parameters that we have here, it's not a very good. The prediction is not very good. But let's visualize the results. We are creating a range of X values for plotting the prediction line. It generates 100 H values from the minimum of X value, which is the minimum observed age, to the maximum observed age in the data set. And this will be used as the X coordinates to draw a line to represent our model's predictions. And then we can create a figure. and we create a scatter plot. We are selecting everything at column index 0, which is the first column, and then Y value. And so this will plot the actual rabbit data that we have. Each dot will represent one rabbit with its age on the x-axis and the lens weight on the y-axis. Then we need to plot our Adaline model's prediction line. So the way we're plotting the Adaline's model's prediction line is here. Here, the X range are the 100 evenly spaced age value we have created here. And this weights 0 plus 1 multiplied by X range. This is the core of the Adaline prediction. W0 is the bias term that was learned by Adaline. And weight 1 is the weight for the age feature, W1, that was learned by Adaline. So, this expression calculates the predictive y value with W0 plus W1 multiplied by age for every age value in the X range. Because X range is a NumPy array, so this operation is performed element-wise. And in the end, we have the result is an array of 100 predicted lens weights. And that's the line here. That's the line we have plotted here. And as you can see, it doesn't adhere exactly to the trajectory of the original data. And that's also the reason we have a very high MSE value here, and the weight is very small compared to the bias. But of course, we can make we can change some hyperparameters here to make it, for example, we can add more iterations, but it's gonna take longer time. You can see already we have reduced the MSE by a lot. But that's the simple implementation of the first task. We implemented the Adaline algorithm ourselves. And for task 2, we can use our own implementations, or we can use existing implementations. You can use any libraries you want, of a multi-layer neural network to predict the weights of the eye lenses from rabbit's age. You can use scikit-learn if you're using Python, or you can use NStar if you're using MATLAB. And then we need to do the following task. We need to create a separate training and test sets from the data. And this is very common in machine learning because We explain it later. So we train the neural network on the training set and evaluate accuracy on the training and testing sets. Is this we should compare, is this better than Adaline? We need to visualize the prediction results, and it also give us how the rabbit data was modeled using this regression line, where uh this is the error term. Compare our neural network against this model. Which one is better? Then we should modifying our architecture and reach overfit and underfit. How explain how you can tell is overfit or underfit? Visualize one example of overfitting and underfitting. Then we apply, after we have reached overfit and underfit, we apply normalization on the data. And this is the normalization formula. We return training and evaluation. Do we get a lower prediction error using this normalization method? Was the training faster? Why so? Okay, for this implementation, we'll use existing implementations from scikit-learn. The first one we'll be using is multi-layer perceptron regressor. And we'll use this library for train test split. So we're using this library, but we will configure its architecture, such as the number of layers, the neurons per layer, activation functions. Then we will train it using this library. And we'll also use this train test split to create separate and training and testing set from the data, as it is required here in the task. But first, let's define our model. Okay, we have a couple of parameters here, a couple of arguments here. We have our chain X, chain Y, which are the features and the target values, and text X, text Y, the same, but they are the testing sets. Then we have here our keyword arguments. This allows us to pass any additional parameters directly to the MLP regressor. So for example, we can call this function, then we can just add any parameters we want here, such as for example, hidden layer sizes or activation equals ReLU or any parameters you want, and this parameter will be used to define the multi-layer perceptrons architecture. So first, we initialize the MLP regressor model. And the keyword arguments are unpacked here. So we pass any parameters that we want directly to the MLP regressor. Then we need to train to fit the MLP model. So the fit method trains the neural network using the training data. It adjusts the network's weights and biases to minimize the prediction error on this data. And then the model is returned and reassigned to the MLP variable. We also wanted to print out some training information and performance metrics. Number of iterations. So we can see how many times the model has gone, how many iterations the model has gone through, so we can compare the results. Then we also want to know the MSE value. And to calculate this, let's see if this formula is correct. Uh, predict train X. Here we're getting the model's prediction for the training data. Then we minus the train Y, which are we're calculating the difference between prediction and the actual values. And then we square these errors. We square the errors. And then we calculate the average of these squared errors. So that's the correct formula to calculate and print the mean squared error on the training set. And then we did the same thing for the testing set. After that, we need to prepare the data for plotting the model's prediction line. Again, we are creating evenly spaced x values ranging from the minimum to the maximum. And we are getting the MLP model's prediction for those X range values, and then we are reshaping them into a two-dimensional array with one columns, because that's the expected input format for scikit-learn's predict method. And then we need to create the plot. We initialize the plot, a plot for plotting. And then we need to plot the training data points. and we give it a color of blue. And we label it as training data. Then we also need to plot the same for testing data points. So same goes for same goes for the testing plot. But here it's giving it a color of green and label it as test data. And then finally we need to plot the model's predicted line. Okay, this is the architecture we implemented. Basically, we just pass through the data, train it, and then we create a plot. Then we can start our exercises. First, we need to create separate training and testing sets from the data. Okay, then we can start to call the function and train our model. So the first one we're gonna try is just go through the model directly, the architecture directly, without any normalization. So for activation, we can use 10. Um, so we're calling the function we have defined earlier, and we are passing the train x, train x, train y, test x, test y. We have created here. We split the data, and then we are putting them through the model. We set the activation function to 10. hyperbolic tangent. So the squashes its input to an output range of minus 1 to 1, and it's a very common nonlinear activation function. And the hidden layer sizes we define here is the architecture of the MLP. So it means we'll have one hidden layer, and that hidden layer will have two neurons. We'll have two neurons, one hidden layer. So this is a very small neural network. So let's see how it's gonna go. The solver we have chosen here is LBFGS. So this is a specific algorithm that's used to optimize the network's weights. Um, this optimizer is often effective on very small data sets. So it's useful when you want faster convergence for very simple problems. And lastly, we have a parameter of Nestoroval's momentum. We set it to false. And the Nestoroval's momentum is a technique that's used with some solvers, such as stochastic gradient descent, SGD. It can help to accelerate training and avoid local minima problems, but it's not typically used with LBFGS. So that's why we need to set it to false. Okay, after we have used the model to make the predictions, then we can generate our X values for plotting. Again, we're creating 100 evenly spaced points for X. Zero point zero zero 604 multiplied by X range. And you can see the regression line here. It's from here. So we're plotting the given linear regression line here on the same plot. So we can compare the MLP's learn curve with this specific nonlinear model that was provided in the problem here, the regression line here. So we can compare the results. Okay, and we have our neural networks here, the result of our neural networks here. We can see the red line. The red line is the prediction, and the blue line here is the original nonlinear regression line. And we can see the MSE is pretty low. It's around 667 on training set and 106 on testing set. And this is reached by 122 iterations. So this is a pretty good result because the line follows closely. But let's try it a few times more. This time we get 2 iterations. And the prediction line is very far off from the original line. And we have a very high MSE here on train, also on test. And we just run it multiple times to see the difference. So the reason why we are seeing this difference after each run um, is because the neural net the weights are initialized with a very small random values before the training begins. So this specific set of initial random weights determines the starting point of the optimization algorithm on the error surface. So if you're thinking about this landscape of data, we are trying to find the lowest point on this map. So the different starting point can lead the optimizer down to very different paths towards a minimum. Some starting points might be, if you are very lucky, then they are very close to a good solution, or they're on a very smooth path. So it will lead to a faster convergence. If you're unlucky, then your starting points might be very, very far off from the lowest point. So then your model needs to explore more and to explore more with more iterations. And you might also be wondering that we didn't set a specific number of iterations, and the number of iteration changes here. It changes every time we run it. It's because of because the solver we're using LBFGS. So this solver, it's like most optimization algorithms. It doesn't just run for fixed numbers of iterations. Instead, it will run like a certain convergence. It runs until a certain convergence criterion is met. So either it hits a maximum number of iterations, or it has some criterions that's controlled by the tolerance parameter. So the training will stop when the loss or score is not improving by at least the tolerance value for the number of iterations, which the default is 10. So for 10 consecutive iterations, if the loss is not improving by the tolerance score, then the training will stop. So if the initial weight happened to place the model in a part of the error surface where it quickly find a spot where the improvements are smaller than this tolerance parameter, then it will stop very early. But if the initial weights led to a longer, more complex path before this stable point is found, then it will take more iterations. So the error surface for the neural network is very complex, and it has many, many local minimas or flat regions or saddle points. So that's why the tuning of the parameters is so important here, because we want to overcome the local we don't want our algorithms to be stuck in local minima. Okay, so to compare our neural networks against this model, the original model that was given in the task, which one is better? So I can see, the result is pretty good with 75 iterations. Um, we have a pretty accurate model. And then we should modifying the our neural networks to reach overfit and underfit. Let's make some adjustments to our model to deliberately give it to make it overfit. So maybe here we change the neurons and we give it a very big number for max number of iterations. So, okay, maybe let's first discuss what is overfitting. So overfitting occurs when a machine learning model learns the training data too well. So instead of learning the general underlying pattern in the data, it starts to memorize the specific details and the noise, even the noise that was present in the training set. And how can we see if a model is overfitting? So this model will have excellent performance on the training set, on the training data. The model will have a very low error, extremely low error when making predictions on the data it was trained with, but it will have a very poor performance on unseen test data. So when the model is giving new data that it hasn't encountered during training, its error will be very significantly higher. So that means it has failed to generalize its learnings to new situations. So it just means it's memorizing all the stuff that it was encountered during training, and many things could contribute to this, to um, why the model is overfitting. And a common one is that it has a very large, uh, very it has many hidden layers with many neurons. Because the more neurons you have, the more information the model can store in its hidden layers, and it's easier for it to memorize everything that it was trained with. So when the model is overfitting, the plot that you see, the prediction line will look a bit too complex. It will wiggle a lot to pass through almost every training points. So it's not capturing the smoother general trend of the data, but rather it's fitting everything into its model. And that's what we're seeing here. You can see the line wiggles a lot. It's not a smooth line. It goes up and down here because the model is it has memorized at this point, the number should be this. Um, and a few parameters that we have added or modified to reach this overfit. Um, so important parameters are we have discussed here the hidden layer sizes. Here we are giving it 50 neurons instead of 2 like we were using before. Compared to smaller networks, it has it has more capacity, so it has more parameters. It can learn more complex functions. But for this simple data set, for this our data set is very simple. So it has a lot of access capacity, which allow the model to fit the noise and the specific details of the training set. So the number here should really depend on your first of all, different researchers, they have different preference on how big the how many neurons there should be. And also it heavily depends on the data set sizes. Also, we've given it here a very large number for maximum numbers of iterations. So by setting this very large number, we're given the optimization algorithm a lot of opportunities to continue adjusting the weights and minimize error on the training set. So with this enough iterations and sufficient model capacity, the model can drive the training error to a very, very low value. And that's also essentially memorizing the training set. So if this were a smaller number here, I think we have a maybe 1 million. Even though it didn't run 1 million at the end, here it run 12,000, 13,000, around 13,000 iterations. But just by giving this optimizer ample opportunity to memorize, um, we have reached overfitting. So if the max number of iterations were a much smaller number, the training might stop earlier due to the convergence criteria already met. For example, earlier the convergence, yeah, here the convergence criterion actually met around 133. That's why the optimizer stops and didn't continue. But here, because we're setting it to such a high number, it didn't stop and kept running and memorized the training set. Also, we have here alpha. We set it to 0. Alpha, the alpha parameter is a L2 regularization parameter. And regularization is a technique that's used to prevent overfitting. And how is it preventing overfitting? It's because it's adding a penalty to the loss function for larger weights. So like to put it simply, a larger alpha encourages smaller, simpler weights. And therefore you will have a smoother, a less complex model. And by setting this alpha value to 0, we're turning off the regularization entirely. So it's not giving penalty to the loss function for larger weights. And without this penalty, the model's weights it's free to grow as large as it wants, as large as it needs to fit the whole training data as closely as possible. Um, and that's how we got this wiggly function that's very specific to this data set. And this is a very clear overfitting example. So next we need to reach underfit. We're using the same data as before, but we're changing a few parameters that we have discussed before that's key for overfitting or underfitting. Okay. You can see we have changed a few parameters here. Um, the neurons, the max number of iterations, And yeah, I think that's all we changed. So underfitting occurs when a model is too simple and when it's trying to capture the patterns in the data. So it fails to learn the training data well. And therefore it performs poorly when it also performs poorly on unseen test data. Because the model is not complex enough to represent the true relationship in the data. So underfit when you have an underfit model, you will see a very poor performance. Like here, we have a very high MSE, mean square error, even on the data it was trained with. Like this is MSE on the training set. Even on the training set, it has a very high MSE. Um, and for the visualization, you might often see a curve that's very simple, that's or too simple because it doesn't follow the trend of the data points. Here we just have a straight horizontal line here. It's not following the trend of the data. And how we achieve this? We change two parameters, the hidden neuron, hidden the neurons. Here we only have one neurons. Opposite is here we have the complete opposite of overfitting. Here we have just one single neuron in one single layer. So it has an extremely limited capacity. It can only learn very simple transformations in the input data. So even if the relationship between the rabbit age, between the age and the weight is slightly nonlinear, a single neuron does not have enough capacity to model it effectively. So it's almost trying to like to fit a very complex curve with a very slightly bent line. And that's what we have got here. Also, another parameter that's very important for underfitting is you have set the maximum number of iterations to to a small number. Because by setting this very small number of iterations, we are restricting the training process. The optimizer algorithm just does not have enough time or enough steps to adjust the network's weights sufficiently to find a good fit. Like even if we had larger capacity, the training will stop prematurely because the model just didn't have enough chance to learn. And here the alpha value doesn't impact this directly. Um, it doesn't so it doesn't help prevent underfitting. The primary drivers of underfitting here are the tiny network and the training iterations. And lastly, we need to apply normalization on the data and return the training evaluation. Lastly, we need to implement normalization. Here actually is giving you some suggestions to import this standard scalar, but because it has given we have this formula here on how to do normalization, so we're gonna implement ourselves. Uh, Firstly, maybe a simple explanation. Normalization is a very common processing step in machine learning, almost, and it's also the best practice to do so that you normalize the data. So it basically it means it transforms your data so that each feature has a mean of 0 and a standard deviation of 1. And the formula where we are using here is this one. The normalized, or some people call it standardized, x equals x original, the original x, minus by the mean of x, and then it's divided by the standard deviation of x. And that's the simple formula we have. And the result is you get a mean of 0 and a standard deviation of 0. So by applying normalization, we usually will get faster convergence and more stable training, because many algorithms, like, for example, gradient descent, including the ones we have used here, LBFGS, or other gradient descent variants like Atom, they work better when input features are on a similar scale. So if the features have very, very different scales, for example, one feature ranges from 0 to 1 and another ranges from 0 to 1 million, the error surface, imagine the error surface, it can become very elongated. So it's very uneven. You have very, very tall points and very, very low points. And this means the optimizer might take small steps in some directions and very, very large steps in other directions. Um, and this kind of oscillation will make it slow to find the optimal solution. And by applying normalization or standardization, we bring all features to a similar scale that's around 0 with a unit of standard deviation. And this will often give you a more well-behaved or more even error surface. And this can help the optimizer to converge more quickly and reliably. It also prevents features with larger values from dominating. Um, because in algorithms that involve calculating distance or weighted sum, features that have a very large numerical value can dominate calculations, even if they are not like more important, but just because they have very large numbers. Mm, uh, Even just because they have larger numbers, it will dominate. So standardization ensures that each feature contributes more equally to the learning process based on the actual information content and not just the scale. And also another benefit is that it helps with weight initialization and regularization. So common weight initialization assume the inputs are roughly centered around 0 and have a univariance. That's why when we initialize, like probably in all of our formal exercises, when we try to initialize, can we find it here? When we initialize weight, initialize weight, we multiply them by a very, very small number, 0.01. We've done this many times before and that's also because common in a weight initialization, it assumes the inputs are roughly centered around 0 and it have a unit variance. So regularization techniques like alpha we have discussed here, it's a L2 regularization method, the alpha. It penalizes larger weight. So if the features are not scaled or are not normalized, the optimal weight for features with large values, it will become naturally smaller. And this can complicate the effect of alpha or regularization. And with so many benefits, like this is something that you should do. So many benefits. Um, you can use a library to normalize it, but here we're gonna implement this formula. So to calculate, first we need to calculate the mean and standard deviation from the training features only. And standard deviation as well. Okay, then we need to normalize the training features minus uh, the mean of train X divided by the standard deviation of train X. And we do the same for testing features. As you can see, the formula we use here is exactly the ones we have is given in the task. So next we normalize the y value and we do the same. And lastly, okay, I guess we need to change this a little bit. Train X normalized, train Y normalized, test X normalized, test Y normalized. And just for good comparison, we're gonna use the same parameters that we have here just to compare. Here we have two neurons and no largest number of max numbers of iterations. Okay, so we will remove that. Also, I think we didn't have alpha value turned off. Okay, just for comparison. So we use the same parameters that we have here. We have done it at the beginning. And let's compare the result. So this is also a very accurate model. We can see it follows the general trend of the data and has a very low MSE, and also the MSE is also low on the testing sets, around 0.01. So that's a lot lower than the mean square error here, which is around 67 and 106. And also the number of iterations also reduced a lot, because here, if we want a somewhat good result, we need maybe around 100 iterations. But here it reached convergence around 70. And let's run a few times more. This time we have a very low MSC around 58. And now 35. And that's the benefits of normalization. So we have here, to answer the question, do we get lower prediction error? Yes, we have very low MSE. Uh, That means we have a more stable, more reliable, more accurate model. But okay, also, sorry, we actually cannot compare these two directly. We cannot compare these two values directly. That was my mistake, sorry. Because here we don't the MSE is this one is not normalized. It's not normalized. Here we have normalized the data. That's why the MSE is on a different scale. So we cannot compare directly the values, but still we can see but still, do we get a lower prediction value? It's yes, because um, the MSE without normalization, because the scales are different, we cannot directly compare. Um, but the relative improvement or generalization, we look at the general trend of the graph. They are accurate. They follow the general trend of the data sets. And the mod convergence to a good solution, the model trend on normalized data might converge to a solution that if you were to unnormalize its prediction, then calculate the MSE in the original units, it will be lower than the MSE from the unnormalized data. So when we normalize data, the training process itself is often more stable with normalized data. So it's less sensitive to choice of hyperparameters like learning rate. And the we also just by inspect this visually, it's an accurate model. So in many cases, normalization help the network learn more effectively, leading to what can so this is considered to be a better model. And another question here is, was the training faster? So means it requires less iterations to reach the same accuracy. And this is a definite yes, because the model has reached convergence around 30 instead of 100, like around 100 iterations that it requires here. And this is due to how optimization algorithms work, particular, especially gradient-based ones like LBFGS. Um, since we have a more even, more conditioned error surface, imagine the process of finding the best ways as navigating this landscape to the lowest point, and that's called the minimum error. If you have a very different scales, then the landscape is very um it has a very high points and low points, so it will oscillate a lot. And standardization make this even more even. That's why the gradient optimizers that use gradient descent will have more uniform. It will have more uniform gradients. Then the learning process um, is faster. Then the learning process is faster and smoother. Uh, and the activation also, sorry, the activation functions like tan and sigmoid are sensitive when their input is near zero. If the inputs are very large due to unscaled features, then these neurons can saturate. Their output barely changes, even if their input changes significantly. So this will lead to a very smaller gradients, which are what we call vanishing gradients. Okay, and that's why we have that's the answer to the questions. We have applied normalization to the model before we put it through this MLP regressor. Okay, I think that's it for today's exercise. Please let me know if you have any questions and regarding the course, the exercise today. If you have anything that you didn't understand, any concept that you didn't understand, and a very gentle reminder, please register yourself for the presentation on Wednesday. The registration closed yesterday, but now we are extending one more day. So you have time to register yourself or for the group for the presentation on Wednesday and Thursday. Okay, if you don't have any questions, then that's it for today's session. Thanks everyone for coming. Thank you. And please register for the presentation. Thank you.